Yinyu for several years, but I never meet her in person. I kind of know her work at MIT when I present her work in our journal club. So let me give a very quick introduction of Yinyu's background. She is a very excellent researcher. He got a BS degree from Tsinghua University in Beijing. Then she worked with Jason Petta in Princeton to pursue her PhD. And at that time, her great achievement is she used a double quantum dot to create a laser, which is in the microwave range, so we call it maser. Okay, it's a reverse process of photo assist tunneling in quantum dot system. So they use the electron transport to create to jump into different energy level, create a microwave, and internally, eventually like create like a bouncing between the cavity and make a maser. And then she finished her degree, then joined Amir Yacoby's group at Harvard. And since then, unfortunately, I did not learn much about her recent work. So I'm also quite excited to know the second topic of her talk today. So she is now a postdoctoral fellow in Amir Yacoby's group, which is also a world-leading researcher in many different fields, actually, in spin qubit, in Majorana fermion, in fundamental research. I personally listened to Amir Yacoby talk several times. I consider him as one of the smart person I ever met in the world. So I'm very excited to learn Yinyu's work from his group as well. So let's give a very warm welcome to Dr. Yinyu Liu to share her work today. Thank you.
Thank you very much for the introduction. So I mentioned that my research interest is in quantum information processing that's based on semiconductor quantum dots. So before I start, let me quickly review the background. So quantum information has been a very hot topic recently due to the fast algorithm that is promised by the processing, and that of course interests a lot of people and even companies. So for example, this is the 53 qubit device from Google, and they demonstrated a very high fidelity single and 2 qubit quantum gates, and they also saw that the quantum superprimacy problem. But however, in that paper, it's still a specific problem machine. It means there is still a little bit away from the universal quantum information. And the basic unit of the quantum computing is so-called quantum bit, which actually allows a linear superposition of 0 and 1 state. And in classical, you could only be 1 or 0. And the real power of the algorithm, of course, they still rely on some basic requirements. The algorithm actually wants the entanglement between the qubits such that people can perform the single and the double qubit gates. And of course, there was other requirement, for example, long coherent lifetime, such that the information can be stored. And also there need the high fidelity readout of the gates. And then in the end, for the communication purpose, we also want the ability to transfer the quantum information to the so-called Phi qubit. And for this highlighted 3 reasons, then the electron spin that's trapped in the quantum bit is kind of ideal. And the solid devices can also couple the quantum bit to the photons to serve as a Phi qubit. Excuse me. And this system typically used is the circuit QED system. So it is the first demonstrated in superconducting system where people place the the superconducting bit inside of the superconducting coupling waveguide. And there they demonstrated a strong coupling region where the information swap rate between the photon and the quantum bit can be faster than the decay or decoherence of the photon and the qubit. And based on that, people also performed the surface code with 5 qubits that is in array. And in the meanwhile, the electron spins that's trapped on the semiconductor quantum dots is also a very promising system due to the long coherent lifetime that has been promised and the ability that people can place the qubit at anywhere they want on the solid state devices. And then the system motivates people to hybrid this together, and it has been first demonstrated by Carl Peterson, showing that there was a coupling between the quantum dot to the cavity photons inside of the coupling waveguide. And my work during my PhD focused on the photon emission when the quantum dot is biased. So this is a kind of a scheme of my system. So here is the demonstration of my quantum dot. Then I apply a source driven bias, which would kind of constantly driven the electrons to tunneling through my double quantum dot. Then the tunneling event between the two discrete levels need to emit into the environment to compensate the energy loss into either a form of photon or phonon. Then from the emission, actually, we can also detect the dynamics of my quantum dot, and we just hope from by studying the photon emission, we can also learn back how the quantum dot can interact with the noise source, such as the phonons in the system. So I'm going to quickly go over my device structure, then going to demonstrate that the system did emit into the cavity. And if the emission is strong enough, then we can go beyond the Miller threshold to trigger the coherent emission. And if our emission is strong enough and the cavity loss is small enough, then even a single double quantum dot is enough to trigger the Miller threshold. And in that case, we can achieve the so-called single atom maser. And that threshold can tell us a lot about the dynamics of our emitters. And of course, this system is going to be very useful because like it emits coherent and strong microwave on trip. And we can basically utilize that to detect the, for example, we can detect the quantum states of the other qubit that is located on the same trip. But I think this is probably a little bit too detailed, so I'm not going to go in detail in this talk. So our quantum dot is made by the homegrown indium arsenide nanowire, which is kind of between like 50 nanometer to 100 nanometer in diameter. Then we place it on top of 5 bottom gates. And then we further place the source and the drain contacts in order to allow electron to tunneling on and off the quantum well. Then the 5 bottom gates can create a quantum well inside of the nanowire. And if the confinement is good enough, then it can lead to the charge number to be a good quantum number. And in this situation, then if we the quantum dot is going to be trapped in the so-called Coulomb blockade. And in this situation, then transport is mostly forbidden unless the two chemical potential of the quantum dot is within the transport window that is set by the source and the drain contacts. And the cavity we use is the niobium coplanar waveguide. And we are working with the first mode of the waveguide. And the waveguide is coupled to the input and output port through the capacitors. And then we place our quantum dot at the antinodes of this waveguide. And then for the double quantum dot, that will form a dipole moment. And that dipole moment can interact with the electrical field. And that is going to lead to the coupling between our dots and our cavity photons. And then if we apply a source bias through a bias T, then electrons are going to forced to tunnel through these barriers. And in this situation, they can serve as the quantum dot gain medium. So to detect the cavity response to our system, we shine the cavity with the input tone with a power P in and at the frequency F in. And then the output of the cavity is first amplified, then demodulated by comparing it to a local reference to the in-phase and the quadrature components. And these two components you can you can think it as the real and the imaginary part of the complex oscillation amplitude. And from there we can learn the phase and the output power. And by comparing the output power to the input power, we can define the gain coefficient. And here C is a constant to set the bare cavity response to be 1. So we first look into the situation when the double quantum dot is at 0 bias near the charge transition. So near the interdot transition in this case can be simplified into a two-level system. And the energy splitting is basically determined by the tuning between the two dots as well as the interdot coupling. And then the entire system Hamiltonian also need to include the dipole interaction term plus the cavity term. And we further include the relaxation rate of the double quantum dot and the cavity loss rate. Then the input-output theory can basically fit to our data at several different medium gate voltage. And that basically can tune the interdot coupling. And from the fitting, we can find actually there is a good agreement between the theory and our data. And we can also estimate the dipole interaction strength to be around 25 megahertz. And this is kind of similar to all the interaction to the other hybrid systems between the double quantum dot and the cavity. And now we are going to apply a source stream bias on the quantum dot. And in this case, then the bias is going to open the transport window, which can be represented by the two gray triangles in the charge stability diagram. So for example, if we are sitting in this triangle, then one electron is allowed to start from the right dot, hop to the left dot, and then leave the quantum dot, allowing another electron to hop to the right dot and restart the cycle again. And the similar transport cycle is also going to happen at the other triangle, but just cycle through the other charge state. And that means actually inside in these finite bias triangles, we are expecting the finite current. And of course, here that outside of these two triangles, we also measure the current. That is basically due to the higher order tunneling event, because in this tuned up setting, all the barriers are quite open. So the electron can actually tunnel through some virtual process. So the tunneling between these two discrete levels actually has to emit as a quanta, either in a form of phonons or photons. And in order to detect the emission into the photon field, then we place the quantum dot inside of the cavity. Then we first directly measure the photon emission rate by a spectral analyzer. And then there we can find actually inside of the finite bias triangle, there are hotspots where the photon rate is around 10 megahertz higher than the detection noise background. And that actually corresponds to 2 photons inside of the cavity. And then we further probe our cavity with the input tone. And there we found actually the gain of the transmission power at the cavity resonance is going to be 16 times higher than the bare cavity response. So this basically means something is emitting into the cavity. And if we further measure the gain as a function of the input frequency, then we can also measure the narrowing of the line width of the power transmission, which is kind of expected in these kind of fine highness cavities. So we're kind of wondering how far we are from the maser action. So to quantify that, we usually directly compare this simultaneous emission rate to the cavity loss rate. If this photon generation rate is slower than the cavity loss rate, it means the photons will run away from the cavity before new photons are generated. And in this case, we are expecting the thermal spontaneous emission with the photon number that it can be simplified by this normalized inversion ratio. And if we probe the cavity with the input tone, then the gain as a function of the input frequency is expected to be a Lorentzian, and which is kind of in a good agreement with our data. And from the fitting, we can calculate our inversion ratio is around 0.7 to 0.8. And that will estimate around 2 to 3 photons inside of the cavity, which again is in agreement with our data. So this number seems to be very close to 1. And what will happen if the normalized inversion ratio is larger than 1? And in this case, it means the photons will stay in the cavity and the new photon is going to be generated. And in this case, then the photon is going to start accumulated inside of the cavity until it drains the gain medium. And in that case, it is going to generate the strong coherent emission, which is also called maser. So it seems like we are very close to the threshold with just 1 quantum dot. Then the simplest way for us to go beyond the threshold is place another emitter into the cavity. And in this setup, we first characterize the bare cavity response. And there we can find the quality factor around 3000 with the center frequency to be around 8 gigahertz. And then if we only turn on the emission from the right double dot, then the gain is around 6. And then emission from the left dot is going to increase the gain to be around 16. But however, if we have the emission from both the double quantum dots, the gain can be as high as 1000. And this is way much higher than if you just times the emission from the left and right quantum dot. And we start to work.
Yeah. Is there any reason that the peak has shifted a little bit in frequency?
So that is called the cavity pull effect. That is usually due to the energy splitting of the quantum dot itself.
Okay.
So usually the so-called cavity pull, it is because your system, first you have your cavity, the resonant frequency. And then the quantum dot or any atom inside of the cavity, it has its own energy splitting. And usually in the end, the laser frequency is going to be the combination of these two frequencies, and that ratio is determined by the loss rate of the two systems. I didn't place the equation here, but there is a math to calculate that.
It's not nothing to do with the James Cumming model. You have a two-level system coupled, because in my imagination, it's only the quantum dot electron transmission will emit the microwave at the same frequency of the cavity you design, and then somehow just enhance the gain. But I just wonder, there's nothing to do with the James Cumming model. Is it correct?
So,
because in superconducting qubit we see that you have an atom coupled to a cavity, you will shift that.
It's not related to that. I think in that model it is already in strong coupling region, right? And that shift is due to there is kind of the avoid, or you can call it avoided crossing, because it is in the strong coupling region, and then the coupling is going to open a gap there.
Okay.
But in this system, it is way below the strong coupling region, so the dispersive model still works here. And I didn't really go into a very much detail of the of our first work, actually, which studies the kind of the detuning and the emission. And in that situation, usually we found actually the strongest emission peak. Usually it's not necessary where the double quantum dot energy splitting equals the cavity rate.
Okay.
So that actually, I think it's one of the reasons why, if we want to achieve the strongest gain, usually the quantum dot is kind of detuned from the cavity resonance frequency, and that is going to create this cavity pool in the emission in the end. But I think the system that we are studying is kind of more complex, because it's also coupled to the phonons background a lot, and our emission process is actually also more dominated by the spontaneous emission process, where the tunneling event is going to emit one photon and one phonon at the same time.
Okay.
And in this case, it also depends on your phonon spectrum or etc. So, but to answer your question, it's not really related to the James Cumming model in this system.
Yeah.
Okay.
Yeah. Okay.
So basically, I think the you can just only consider the real part of the of your term, because usually the imaginary part will correspond to the frequency shift or phase shift. But usually, in this semi-classical models, you only need to consider the real part of which corresponds to the loss or gain coefficient. And the system should be enough, should be simple enough that you just add this gain all together, that is going to create the total gain of the medium inside of the cavity. But however, if we have two gains in the system, it seems like there is a shoot up of the gain of the system. So that is usually a signal of we are probably go beyond the major threshold. And in order to study that, we first want to look into the spectral emission when there was no cavity drive. And in this situation, actually, we can find that there was a kind of very clean emission peak, which is measured by the spectral analyzer. And by calculating all this gain efficient in our detection train, we can estimate around 8,000 photons in reference to our detection train input. And the line width is also 100 times narrower than the cavity line width, and the coherent time and the coherent length seem to indicate it is kind of a good coherent source. But however, if we want to compare it to the Charlotte's limit, it is still 100 times wider. It is very typical to a solid devices, though, because usually these devices suffer from the charge noise a lot. But in order to really tell whether we are in the coherent emission, we need to look into the phonon statistics. So In the in phase and the quadruple phase, if we are a thermal source, then we can kind of imagine the emission is kind of just perform a random work around 0, and there we expect a Gaussian distribution in the in this 2D plane. But if it is a coherent emission, then we expect a constant like displacement from the origin, and then the distribution should be a donut shape, and which is the case of our data. And if we looked into the photon number distribution, which is extracted from our data by comparing the histogram to a background, and we found it is still way much wider than the Poisson distribution, which is the ideal coherent source, and instead actually it fit to a Gaussian better. But beyond that, you may also notice there was a thermal emission kink, which indicated like 3% of the chance that the system is a thermal source. If we look back into the distribution, actually it's more obvious. You probably already noticed there is a white dot in the donut. But if you do a line cut around 0, then we found beyond the two peaks will actually correspond to the ring structure. There is also a Gaussian bump in the center. So that actually is the caused by the charge noise, which is sometimes is going to shift the quantum dot level from the most ideal gain situation. And in that case, then it's going to cause a lot of fluctuation in the gain of our medium, and sometimes the shift is so large that it is going to turn off the emission a little bit. And here is a time trace of the in phase. We can notice that it is oscillating. Sometimes there is a lot of fluctuation in the amplitude, and sometimes it just turn off completely. So here that we demonstrate that we can achieve the Maser action by coupling a cavity to two double quantum dots. And the more interesting things are expected if we can reach the single atom Maser limit. And in this case, the interaction between the gain medium and the cavity is the simplest case. And there is also a lot of like the non-classical quantum photomic phenomenon can be observed in this limit. And in order to achieve that, we first redesign our cavity, and we add a lot of filters to reduce the RF loss through the double quantum dot contact pads. And we also have a better E-beam tool, which can bring the source and drain context together. And that is going to basically increase the local cavity field that can be seen by our double quantum dot. And in the end, we kind of doubled both our quality factor of the cavity as well as the dipole interaction term between the double quantum dots and the cavity photon. And in this case, then we can achieve the Maser action with only one double quantum dot.
I read this paper yesterday, and I wonder what are the features, for example, just before you enter the bond pad. Are these winding lines, or you know what I mean? There's a bond pad, and before that, there's a, no, below, yeah.
Below?
Yeah, just below the bond pad a little bit.
You mean here?
Yeah. What are these features exactly?
They are, so okay. So the bond pad here, it is actually a limited inductor.
It's like a square. It's a squared inductor.
Yeah,
I see. Yeah.
And here it is a capacitor.
It's a capacitor.
Yeah, here it is a capacitor. So it is like the common feature of capacitors.
Okay.
So here, all this kind of purple, they are niobium.
Yeah.
And this color is gap. And here it is a very dense capacitors.
When you mean capacitor, it's still connecting to your gate, which you can apply voltage, right?
Yeah, so it is the capacitors. One end is connected to the contact pads, and then the other pad is actually the ground plane.
Okay, but you need one of the feature to use as a source and drain, right? You have a source connecting to the center LOC filter, that part, yeah, that's right. And you have a drain that need to need to connect. So that one is not capacitor because you do need to measure current, right?
So the current is measured. I can go a little bit more detail in this. So this node is the center is all the way connected to the center of the capacitor. So the central island of the waveguide.
Yeah, that's right.
And then the drain is actually connected to one of these pads.
So that drain is connecting. It's not. There's no capacitor.
Oh, I see what you mean.
Yeah. Capacitor means it's not conducting, right? Is that?
So the capacitor is actually to the ground plane. It is a very large capacitor to the ground plane, but the line itself is.
Okay, that makes sense. That makes much more sense. Otherwise, it confused me. Okay, so it's just a line that has some space between the ground.
Yeah, it is a line with a kind of a very large surface between the ground plane and the line.
Okay. Because I didn't see this feature in your science paper, so that's the new feature that in this PRL, I guess.
Yeah, it is the huge improvement of the system. Because like in my science paper, it is just like the 50 ohm transmission line that's going to connect the contact pads to the to our device. But somehow, like we measure, there was a kind of a 6 dB loss.
I see.
That we think it's probably just the loss is all through this kind of the DC lines, which also like kind of you can say it destroyed the tightness of the RF. So we further increase this kind of filter.
Okay, that's fine. I mean, it's maybe too much detail, but I'm just curious. So okay.
But it's okay.
Go ahead. Yeah, please go ahead. Yeah.
But yeah, more detail is in the PRX actually. But anyway, so yeah, with this improvement, then we can actually achieve the single emission limit, and then we want to study the threshold behavior of the system, which is kind of the last evidence that we are above the threshold. So in this case, we kind of need to tune our gain coefficient. Usually in the quantum cascade link, it is as simple as like you are going to tune the current that's flowing through the device. But however, for the quantum dot, it's trickier because the tunneling rate is only set by the barriers. And if we want to tune the barrier tunneling rate, it's going to destroy or it's going to change the chemical structure of our artificial atom. And in order to solve this problem, to make sure that we can effectively tune the gain of the system without changing the level structure of our quantum dot, what we do is we apply a square wave, which is going to turn the quantum dot levels in and out of the transport window. And during this process, we are going to keep the tunneling rate over all three barriers, as well as the tuning between the two dots at the same. And then the current would be proportional to the duty cycle of the square wave. And if the period of our square wave is going to be shorter than the cavity lifetime, then to the cavity gain side, it is effectively that we tune the electron tunneling rate through our device. And then we first demonstrate the time trace at a different current. Then we noted like there was a turn on of the oscillation emission with the increase with the amplitude that increases with the current. And then this is the movie that we collected the statistics of the system. And we noted at a small current, it is just a noise, which is a wider thermal emission on, and eventually it's going to trigger the maser action and turn into the ring shape. So by directly measuring the output power at a different current, we can find that there was a sudden increase around 100 in the output power at the threshold current. And to understand the threshold behavior, well, we can recall that actually the emission is caused by the single electron tunneling event. And then the emission rate is going to be proportional to the electron current. And there we can define the emission coefficient, which is basically tells you the probability that the electron tunneling is going to emit one photon. And then if we place the double quantum dot in a cavity in this case, then again that we can define the normalized inversion ratio, but which is kind of linear to the the current. And by this equation, we can directly compare our cavity line width to the threshold current, and there we can basically calculate the emission efficiency. But of course, like once it is above the Maser threshold, then it is going to trigger the Maser action. So our data is kind of in qualitatively agreement with the single atom Maser theory. However, the quantitative explanation, we also need to include the emission from the tunneling event that through the barriers. So this is some dynamics that has never been discussed in these emission theories, and demonstrate that how much you can learn from the threshold behavior of our system. However, this emission efficiency is kind of too low to really observe some interesting quantum optical phenomena. And usually that is only observed when this ratio is close to 1. And which I think is in our next stage. So here I think I'm going to briefly conclude the talk of this part. Is first we can find the photon emission, which can trigger the Maser action, and the threshold behavior can tell us a lot if we reach the single emitter limit. And of course, this emission can be very useful to such as like serve like the microwave source on chip. And the line width can also be improved by the injection locking effect. But if we really want to use the photons as a carrier of the quantum information, and then we need to go into the strong coupling region where the interaction rate need to be stronger than both the decay rate of the double quantum dot and the decay of the cavity. And usually the interaction rate is already higher than the cavity decay rate. It is usually hard to beat the decay of the quantum dot. And here there was some demonstration like how people achieve that in a way much cleaner system that is based on the silicon germanium platform. I think I have only 10 minutes to talk about this, and I'm going to go very briefly through this topic. So again, the electron spins, if you still recall the motivator why I studied the double quantum dot, is due to the long coherent lifetime of the electron spin in the system. So for example, in gallium arsenide, it has been demonstrated to be around a millisecond scale. And because that we can define the location of the quantum dot by
you can have 20 minutes. I think that's fine. It's
okay.
It's up to you, but you can have 20 minutes. Yeah.
Then you can kind of define the location of the quantum dots by the nanofabrication, and that actually allow us to bring the two electrons close enough to create the coherent entanglement between the qubits. These examples are all achieved in gallium arsenide, which usually has a way much better quality at the early stage. However, this system has a very heavy nuclear, and which is going to fluctuate a lot in the magnetic field background, and that really limit the coherent lifetime. And that motivates people to start to move to the silicon germanium platform. So this group 4 elements, usually they have 0 nuclear spins by the nature abundance isotopics. And then there has demonstration about single qubit fidelity that's above 99%. And also the 2-qubit gate that's above 90% in Jason's lab. All these examples are based on the single spin. But there is a kind of a huge limit of a single spin because the energy splitting is determined by one external global magnetic field. And if you want to just address the individual spins without impacting others, it is kind of very hard to entangle the environment spins from your target spin. And that kind of make the so-called singular triplet qubit very ideal. And this is first demonstrated in Jason's work. And then that has demonstrated the 2-qubit gate in this platform. And then people also start to study the probability of this qubit candidate in silicon germanium candidate. And then my work focused on basically to achieve the 2-qubit gate in silicon germanium. So why people start working on this substrate later? There are actually a few difficulties. So first, there are value degeneracy in the silicon, and the 6-fold degeneracy can be lifted by 4 by this sandwich structure. But the remaining 2-fold degeneracy has to be lifted by the string between the interface, and as well as like a very careful ground of the system. And also the spin orbital in the silicon is very, very weak. To some extent, it is a kind of a good news because it means your charge noise will not couple to your spin that much. But it also means you cannot control the electron spins by the electrical gate. And that basically means people need the micromagnet in order to really effectively control the single electron spins in the system. The electron mass is kind of large. It means the confinement need to be smaller, but the Fermi C is not in the conducting band. That means that you also need the accumulation gate in order to introduce the electrons into the quantum well. And all of this actually kind of combine the kind of fabrication difficulties. So my work basically address the value degeneracy. In our work, we can demonstrate how we can measure this degeneracy by some spectroscopy. And we also demonstrate actually the value state can actually help us to get enough spin orbital coupling such that we can achieve the qubit control without a need for the micromagnet. So the device we use is the substrate is provided by Mark Erickson in Wisconsin, and then we further place this fine features on top of it. And we use the overlap gate geometry that is first bring up by Jason's lab. And with all this like electron gates, we can confine 4 quantum dots in the order to carry 2 singular triplet qubit. And we can further place the 2 sensing dots in order to perform the charge readout. And we basically use the RF reflectometry to perform the charge readout. And here we demonstrate the charge stability diagram by measuring the reflectometry as a function of the 200 gate. And from the differential, we can see the kind of the charge transition more clearly. And with that high fidelity readout kind of achieved, now we want to study the singular and the triplet qubit. So the easiest way to understand this qubit, we can first go to the 2011 charge transition. And for the singlet state, then the energy splitting of the system is again only defined by the tuning between the two chemical potentials and the interdot coupling. But if the system is in the singlet, then the Pauli repulsion is going to forbid the right electron to hop to the left dot. Then the energy is going to be linear to the detuning. And if we further apply magnetic field, then it's going to lift the degeneracy. And the field gradient or spin orbital coupling is going to further open up avoided crossing between the T plus state and the singlet state. And we usually use the ground singlet state and the triplet state to be the subspace of our qubit. So the first step is we want to verify the singlet triplet are well-defined quantum states. So in order to verify that, we first prepare our system in the 3-0 charge configuration. Then we quickly load an electron into the right dot. And then we go to perform the charge readout in this charge stability diagram. So if the system is in the triplet state, then it will be locked in the 3-1 state, even if the ground charge state is 4-0, and that will give rise to this bright yellow region. But of course, if you go deeper into the 4-0 and such that even the excited state is lower than the right dot, then the tunneling is going to be allowed again, and that is why we have this area to be in the ground 4-0 charge state. So when we observe this, and that means actually the singlet triplet are well-defined charge state at least. And we can also utilize this area to perform the qubit readout to determine whether our system ends up in the singlet or triplet after the qubit operation. Then next, we want to measure the energy splitting of the system. This is usually performed by the so-called spin funnel measurement or the Zeeman splitting spectroscopy. What it does is we want to detect the location where the T plus state and the singlet state they interact. When they interact, it means the exchange energy equals the Zeeman energy. And by that, we can map the Zeeman energy to the exchange energy. And in order to detect the location where they interact, we first prepare our system in the 4-0 state. Then we quickly go to the exchange location. If it's not the interaction location, then the system will always stay in the singlet state. But if it is at the exchange location, then there will be some probability that we are going to end up in a triplet state. And here is the result as a function of the detuning and the field. We can find actually there is an expected spin funnel where we can tell what is the exchange energy by directly telling what's the Zeeman splitting as a function of the detuning. But of course, we also noticed there was other more bright features, which is kind of parallel to the spin funnel. And there are also other curves that with different curvatures and even flipped in response to the magnetic field. To fully understand these features, we need to recall the silicon suffers from the valley degeneracy a lot. And if we are in the deep 4-0 state, then both the valleys and the spins is going to be filled up. But if we further increase the detuning, then the two valleys in the left dot can interact with the two valleys in the right dot. That will give rise to these 4 allowed charge transitions. And then the interdot coupling is going to further open up the avoided crossing. But of course, if sometimes the interaction rate can be even larger than the splitting, then it's going to further hybrid this valid state into this kind of situation. So for the triplet state, then the Pauli blockade is going to forbid this interaction and ends up in the energy diagram that is kind of keep as a constant. Then magnetic field is going to further lift the degeneracy here. So now let's use this system to understand our data. We started in the 4-0 state, and then we quickly go to the exchange location. And this can actually interact with the 4T+ state. And that is going to give rise to this kind of the curvature, which kind of with a constant offset from the first order ones. And that offset is basically determined by the value splitting in each dot. And here we can kind of measure the value splitting is around 10 micro EV and 30 micro EV in each dot. So this is kind of a very small splitting. And
just to confirm, this diagram, the label is reversed, is it? The x-axis should be magnetic field, and the y-axis should be epsilon, isn't it?
Depends on how you look into this.
Okay,
so the real measurement, yes, we set the field, then we sweep the epsilon. Okay. But in order to basically what we want is we want to know what is the curve of this one.
Mm-hmm.
Then we just uniform the.
Sorry, I got it wrong. I got it wrong. Now it's fine. Yeah, it's fine. Sorry, my bad.
Yeah. So it's fine. It's fine. I think it's basically I don't know whether I go too fast or I explain not clear enough. So yeah.
The steam funnel should be symmetry to zero field, and that's right. Yeah, that's right.
Yeah, so So actually, I have this kind of further area here for convenience of the determining there is no other more features there. Then when I know there were no other more features, so I didn't really measure more here. That is the reason why the curve looks not that symmetry.
It's okay. It's my bad. My bad. Okay.
But anyway, so this is kind of a very small splitting measured from this spectrum, and if the electron temperature is around 100 millikelvin, then there is a kind of 10% probability that's going to excite from the ground state to the next singlet level. And then this level can actually also interact with the T+ state with the above 3 triplet state. This is going to give rise to this red curve I indicated here. And it can also interact with the T- state, which is kind of another branch of the triplet state here. And that is why there is some flipped features here. Okay, so it seems this is kind of a complete story here. Now we can utilize this to first measure the value splitting as a function of the gates. And here what I do is I zoom in the magnetic field so that I can measure the energy splitting in more resolution, and I also extend the epsilon, basically the tuning. And there we can find actually the splitting as a function of the gate is kind of in a very similar order that is measured in the previous work. And now we want to see whether this is kind of a good enough qubit. So the sweet thing about the singular triplet qubit is actually you can achieve the two axis control. At the near the zero tuning, then the energy splitting between the singular triplet is determined by the exchange energy. But if we go to the very far tuning where the exchange energy can be neglected, then the system is going to be dominated by the field gradient between these two dots. And that actually will end up in a Hamiltonian with the amplitude and the angle can be tuned by just changing the tuning between the two dots, which is completely electrical controllable. So in order to study first the rotation along the delta BZ axis, what we do is we are going to start in the singular state. Then we quickly turn off the exchange, and the system is going to start to rotate along the delta BZ axis. And then we can read out the rotation rate by returning back to the readout position. And this is the measurement result. Here we can find actually with large enough detuning, the oscillation amplitude is kind of maximized, and the rate is kind of constant. And here it's kind of demonstrated actually it is purely rotating along the delta BZ axis. And at a smaller detuning between like 5 to 10, we can find actually the rotation rate is faster, but the amplitude is smaller. This means that it's rotating along axis that's kind of tuned away from the delta BZ axis. A similar process can also be performed along the J-axis. We just need to add some adiabatic mapping between the singlet to down up and the triplet to the up down states. So usually like along the J rotation rate, it can be tuned electrically. And we're wondering whether we can also tune electrically along the delta BZ axis. In gallium arsenide, this is usually achieved by the nuclear pumping. And so in Amir's lab, that has been demonstrated the tuning can be around 100 to 300 megahertz. But however, in silicon, there is no nuclear background. In order to understand the mechanism why we even see this, we basically look into the oscillation as a function of the magnetic field. And there we found actually the rotation rate is linear to the external field, indicating effect difference around 2 times e minus 4 of the system. And this is kind of in a good agreement with the value difference between these two dots. If you recall that our system is requires the electron tunneling to swap a value when they are hopping between these two dots. And this again is in good agreement with the previous data. So we want to see like it's a good news because like the system usually it actually requires a micromagnet, and we want to see whether we can do this to all devices. And we first just look into the other transition in the system, and this is where we were looking into. And then in the symmetrical configuration, we can also measure that was a very similar rate. Then around 4435, again a very similar number, but there was more surprising things because like we found actually the tunneling rate is actually also determined by the electrode gates. Actually, we can tune the delta BZ rotation rate from 6 to 8 megahertz. And this kind of I think in future it means like it will probably also allow us to do the 2-axis control with the rate in both axes completely electrically tunable. So here I think I run out of the time. A conclusion. We can get the system to work. The next step we want to achieve the 2-qubit gate. Or alternatively, we can go to the germanium host, which has a strong spin orbital coupling. And we are also interested in coupling the system to the secret QED system. Okay, sorry that I run out of the time, and if people want to ask a question, I will take them.
Okay, thanks for the excellent talk. Yes, I think because at Yinyu's Taiwan it's already 11 p.m., so that's like welcome. Maybe 2 or 3 questions. If I saw Ted is in the list. Ted, do you have any comment, Jianyuan?
Oh, hi. Hi, Yinyu. I am Ted. I'm from Tarucha Lab. Very nice to see you and very nice talk. Can I get some numbers from this delta Z that's between the two dots, or which direction that you're planning to either increase or decrease this?
The question is which figure? This one or?
Sorry, delta BZ. So in the current device, are you already planting the micromagnet on the device, or maybe not?
There is no micromagnet. Yeah.
I see. Thank you.
So the field difference is completely set by the G factor difference between the two dots. And that G factor difference is due to they occupy different values.
Okay, I understand. Thank you. Sorry. Thank you.
Okay, I will ask a question. I noticed for your master work, you use all the way. You use indium arsenide nanowire all the way. Is there any particular reason that you choose this? This material or this system?
Yeah. Yes, there was a reason, because like as I probably already mentioned, that our system actually utilized the higher order emission process. Basically, they need to emit one photon and one photon at the same time. And I have to say it's a treat a little bit, because like the real single atom maser, usually they request the photon is the real dominant, and there should be no photon at all. However, we found actually in the system the charge noise is so large, it is very hard to do this like a first order emission process. So we wanted the kind of the help of the photon background. And the indium arsenide nanowire, they are 3/5. So usually they have a very strong pure Zoc coupling between the electron to the phonons. And that coupling actually help us to get this kind of high gain. And I think that is also the reason why in gallium arsenide and also in silicon germanium substrate, although they attribute a strong spin orbital coupling, but once you dare to like introduce this kind of a tunneling event, then the gain is kind of small. The reason is that they are probably the real way to like go into this so-called quanta with like the non-phenomenon, like the quantum optics phenomena, but they lost the gain that we have in the indium arsenide nanowire.
Okay.
Sorry, can I ask a follow-up question about the indium arsenide nanowire?
Sorry?
This is Tim from IOP, and I just want to ask a follow-up question about the indium arsenide nanowires, because we all know about indium arsenide nanowire has also quite strong spin-off coupling, right? Therefore, the field orientation could also have different effect onto the material itself in terms of spin-off directions. And how do you, in a sense, compromise these, or to understand the spin-off effect plus the single triplet transition, like altogether, like, because I mean the field direction does influence the spin-off direction, right?
Okay, so in the maser work, actually, so first I don't use magnet at all.
Okay.
They are pure charge. But to answer your question, because like it's really related to my next steps in my current work, because like now I'm currently working on the germanium, silicon germanium. And in that case, as you probably mentioned, it's very similar to the indium arsenide nanowire. It has a very like the G factor tensor is really asymmetric. And so I think to answer that, so first you probably need some like vacuum magnet in order to make sure that you are always like in the ideal that you want to work with.
Yeah, thank you. Yeah.
Okay. Any final question? Yeah.
I just nice question. So when you treat the dots as the qubit, Are you referring to triplet and singlet S2 level of the system? Is that the case?
So in my previous case, it is charged for the Mesa. And when I use that as a qubit, I usually use the singlet triplet server space.
Okay, I see.
Of course, I think nowadays it's more successful in the single spin situation. But I think for the scale up purpose, then I think the singlet triplet qubit it has its own advantage.
So it has advantage to scale up. Is there
to scale up? Yeah, I think so. Cause like if you want to scale, for example, 100 or 1,000 of these spins, then that has a question is like your qubit has just one energy splitting. I don't think that's very ideal if you just want to control the individual spins without impacting others.
So in this case, how do you do the entanglement to other qubit?
Singlet triplet qubit.
Yeah.
So you can also still like use the so-called the capacitive coupling. Basically, if the system is in, for example, if these two dots are in the singlet state, then there will be a larger portion. It will be located in one dot. But if it's in triplet, it is forced to be flat, and that is going to give a dipole term of the between these two dots, and that is going to also impact the energy, basically the tuning of its neighbor dot, and that is going to introduce a kind of the C phase gate from this energy through the dipole-dipole interaction. But of course, there is a more popular or a kind of a dream or people in the field want to achieve is so-called the exchange gate. Basically, if you have this, this is also why I use this geometry to bring these two dots also very close to each other. And if in this geometry, it is also allowed that there is some coherent interaction between these two dots. And in this case, you can also achieve some exchange gate.
Yeah, okay.
So the basic is like, I can regard the left two dots and the right two dots as individual two qubits when I want to operate that. But if I want to entangle them, then I can bring these two individual dots very close. But during this, in the meanwhile, the system can be very entangled between this dot and its real neighbor. And then you can entangle all of them together because they are all neighbors, and the interaction rate is basically just set by the so-called exchange energy. And this can also be done for the singlet triplet as long as you are in kind of in 1-1-1-1. And then the two spins of these two neighbor dots can also create some entanglement. This is the most straightforward, but also way much harder to achieve without like introducing like the leakage into other subspace or etc. And that's my goal, actually.
Okay, nice.
Okay, any question at all? Like final one, or otherwise we will close up.
Okay, thank you for the invitation. And,
yeah, it's very nice to have you here to present. I'm sorry, it's very late at your time long. But take this opportunity, I would like to say I will invite another speaker related to quantum dot qubit called Professor He Yi.